Today we're going to be talking about something called an annuity. So all of the examples that we've done so far have been one lump sum payment that we're leaving in the bank account and not touching. We're going to be talking about annuities today, which is when you would put in regular payments. So for example, it says Lincoln puts $50 a week into his savings account. So annuities are very common in our everyday lives. I'm sure a lot of your parents have annuities set up or savings set up so that a certain amount of money goes into an account every month or every week or however they have it determined. So we are going to be learning a new formula, obviously. If we have an annuity, we can't just use the same formula as before. A lot of it is going to be similar, but you are going to notice a few differences. So first of all, the annuity formula is a little bit more confusing. Nothing crazy, still just some basic math operations going on. We still have a lot of the same variables. So our A is still for our final amount, and we can call this future value as well. It's totally up to you guys. Our R is new. So our R is taking place of our old P, our old principal. Now we have an R that stands for the regular payment. So if I was thinking about that example above where Lincoln puts $50 into his savings account every week, 50 would be my R. Our I is still our interest rate, and we're calculating it in the exact same way. So that percentage divided by 100 divided by our magic number. And our N is still our number of deposits. So before it was the number of times something was compounded, but it's calculated the exact same way. So years times that magic number. So first example, Megan makes deposits of $300 semi-annually into an account that pays 4% per annum interest, compounded semi-annually. A, how much money will Megan have after 5 years? Now before we start, I do want to talk to you, when we're doing annuities, for you guys right now in this course, you have to have your compounding periods match. So if you're investing $300 semi-annually, the interest also has to be semi-annually. We're not going to do any examples where those two things don't match up. So just to, take inventory of what we have here. In A says, how much money will Megan have after 5 years? So we're looking for our final amount. I do know that the reoccurring payment or the regular payment is $300. And I see the word semi-annually, so I know that that means my magic number is 2. So when I'm calculating my interest, I have 4% divided by 100 divided by 2, so 0.02. And then for N, I have 5 years times that magic number of 2 to give me 10. So I'm going to go ahead and I'm going to plug this information into my formula. Let me just write it out for you guys so that you can see what I'm doing. So A is equal to 300 times 1 plus 0.02 to the power of 10 minus 1 divided by 0.02. Now when you're typing this into your calculator, you need to be doing your brackets first. So the first thing, let me use a highlighter, not a pen. The first thing that you should be doing is 1 plus 0.02 to the power of 10. Make sure you hit equals when you get that answer, and then subtract 1. Hit equals again, and then you can multiply by the 300. Now, if you have a calculator where you can type all of this in at once, that works too. Either way, you need to be getting an answer of 65.698 for the numerator, which obviously we still have to divide by 0.02, which means we're getting a final answer of $3,284.92. So I've answered part A here. Let me just make this smaller so that I can fit it. So we know that in 5 years, Megan will have $3,284.92. Part B says, how much interest has Megan earned? So we know that Megan is making payments of $300, and she's doing that twice a year. So this means that she's making payments of $600 per year. Now, if she's doing that for 5 years, that means that she's putting in $3,000 of her own money. So really, I have $3,284.92, but $3,000 of that was her own, so there's only $284.92 in interest. All right, and in this last example for the day, Miss Goodrow wants to retire in 25 years with $1 million in savings. What regular annual deposit must she make to have the required amount if her account earns 12% per annum compounded annually? So just to take inventory of what we've got going on here, I want a final amount of $1 million. I don't know my regular payment. I'm trying to figure out my R. I know my interest rate is, let me just move this over here actually. My interest rate is 12%, so I can't forget to divide that by 100. And I see compounded annually, so I don't have to do this, but I'm just going to show you just so you know. Annually just means once per year. So this is just going to be 0.12. And my N is 25 times that magic number, which again is just 1. So my N is 25. Now, I'm going to go ahead and write this formula. Now, I'm not solving for A, but I can plug in everything that I know, and I can rearrange for my A. So $1 million is equal to R times 1 plus 0.12 to the power of 25 minus 1 divided by 0.12. So first of all, 12% interest is really high. You would never find anything even close to that right now. But also, compounded annually is pretty rare, so normally things are compounded monthly, which would help me out more than compounding annually. So this question is definitely not what is going on in the world today. So please don't think that if you go ahead and invest this amount for 25 years, you'll have $1 million. Interest rates are definitely lower right now. So my goal here is to get my R by itself. And in order to do that, I need to be taking this divided by 0.12 and multiplying it on the left-hand side here. So 1 million times 0.12 is 120,000. Now, I'm left with 1.12 to the power of 25 minus 1. I'm going to go ahead and I'm going to simplify this bracket here. So these are all numbers, so I'm just going to go ahead and multiply all of that through. And when I do that, I'm left with 120,000 equals R times 16. I want to get my R by itself, so I'm going to divide both sides by 16, and I'm going to get $7,500. So this is saying that if I invest $7,500 once a year for 25 years, I will end up with $1 million.